Okay. Welcome everyone for the second day of the third week. So we will continue this morning today with discrete and causal set world, and we will start with Jerzy Lewandowski, who will tell us about the formal aspects of loop quantum gravity. Jerzy, the time is 50 plus 10, so 50-minute talk and 10 minutes questions. So just to inform you. Yeah.
Okay. Good morning. Let me start with a bit unusual introduction. So my introduction is, just a second, I'm trying to get rid of something from my screen. Okay, so I can see my slides. When we consider diffeomorphism invariant theories, this is, so in physics, there are not many well-established diffeomorphism invariant theories. And on the other hand, general relativity is diffeomorphism invariant. So very often during quantization, this diffeomorphism invariance implies discretization. And this is something which I would like to illustrate on a toy example, which is very simple. However, this is something which happens when we consider more complex structures, more complex cases. So consider a manifold. And now, can you see the upper line on your screen? I'm asking because I cannot see it, but if you can see, then it's fine. I know what is written on this upper line.
Yes, we can see it.
Okay, so consider a manifold and consider some space of functions. I'm not assuming whether they are continuous functions or just some linear space of functions. And suppose that we would like to introduce a diffeomorphism invariant scalar product for those functions. So the product which is symmetric, positive, definite, bilinear. However, we also want it to be diffeomorphism invariant. So if we assume that this set of functions contains continuous functions, then we can very easily prove contradiction. So we can prove that such scalar product doesn't exist. And well, the only example I'm aware of is to assume that actually we consider functions that have finite support. And when I say finite support, it's not compact support, it is finite support, which means that we consider functions that vanish almost everywhere except for a finite set of points. And then for this kind of functions, we can define scalar product to be just sum. This sum X ranges here all the manifold, and we take sum of the products. Of course, this sum is hopelessly infinite. However, since each of those functions, most of the terms in the sum are zero and only finitely many terms survive, and then this gives us the scalar definition of our scalar product. Well, we can also view this space of functions in the following way, that we can consider arbitrary finite subset of finite set of points in M and consider all possible functions on this finite set. And then we can take union of all spaces of functions with respect to those finite subsets. And moreover, we can also notice that if we consider two subsets that consist of same number of points, then those subsets are actually diffeomorphism invariant. So the conclusion is that even though we consider a manifold and a continuum and a creature, and when we also assume the diffeomorphism invariance for some scalar product, then we ended up obtaining some discrete structure. However, notice that this is not discretization. We are not going here to approximate something continuum by discrete structure, those discrete structures, they just emerge from our assumptions. So that leads to two possibilities, two possible strategies. Option one is that we just give up continuum and we decide that we should consider some discrete theories, and maybe those discrete theories in some sense, in some limit, define a continuum, or that we still consider continuum, however we let those discrete structures emerge from our continuum, and then we coherently control continuum by using those emergent continuous structure discrete structures. And there is a competition in literature between the two approaches. So some people use approach 2, some people use approach 1, and very often they think they are doing the same. However, in fact, they are doing different things. Okay, so let me now turn to the loop quantization. So consider, at this stage, M can have arbitrary dimensions. I wrote 3 because it will be the case for gravity, but you can think of M which has arbitrary dimension. Let G be a compact Lie group. We will also use a basis in the Lie algebra of G, and a dual basis. And consider a connection field, which is one form which takes values in the Lie algebra. And the canonically conjugate field will be a vector field. However, in fact, this is a vector density. So this is vector density, which again takes values in the Lie algebra. And they are canonically conjugate, so they have this Poisson bracket, and otherwise A and Poisson bracket between A and A is 0, and the Poisson bracket between E and E is also 0. So now the loop quantization consists in going to path variables. So for every path E in M, so this E is sort of funny letter for path, but it comes from edge. So E's are edges of graph. So that's why we call them E. We denote them by E. So for every path, we consider the parallel transport defined by this connection variable, which is an element of the group G. And for every surface of codimension 1, we consider the flux of the frame variable. And the flux is obtained in this way that one could say that we contract the vector field with the coordinate volume. And due to the fact that this is density, it defines a well-defined n-1 form. And we, in order to integrate it, we also integrated against any smearing function lambda, which takes values in the Lie group. So we replace the connections. So we describe the connections by parallel transports, and we describe the frames by those fluxes. And then now the advantage is that if we calculate Poisson bracket between this holonomy and this, sometimes we call it holonomy if this E is a closed path. So when we calculate the Poisson bracket, then this Poisson bracket is finite. It is again some holonomy. So there are no, so those Dirac deltas they are absorbed by the integrals. Okay, so now what we do is the following. We consider the following functions of parallel transports of fluxes. So we consider arbitrary functions of parallel transports. So such function may be given by some m paths in our manifold, and arbitrary function phi, which is defined on the Cartesian product on G to power M and takes complex values. And we consider functions which are, again, given by some function of holonomies times flux. So these are functions, one may say these are functions at most linear in the fluxes. And in this space of functions, we have the Poisson bracket. So it is like a Lie algebra with respect to this classical Poisson bracket. The next step, a bit formal, but it is good because we would like to be clear about what we mean by quantization. So from those classical functions, we define a quantum star algebra, A hat. So what we do is we consider, so it is given by first by all formal combinations of all the words. So we consider the elements of this classical Lie algebra as letters, and we can write all possible words and multiply by numbers and take all the formal linear combinations. But this kind of algebra, it would be a free algebra, freely generated by some alphabet. But now we quotient it by the relations which are given by the Poisson bracket. So we want the commutator between A and B to be given by Poisson bracket. And we also want this map from this classical A to quantum A to be linear and even a little more. So we want multiplication by a function of holonomies to be consistent with to commute with taking hat. So it doesn't matter whether we first multiply here in this classical algebra, we maybe multiply function by function of holonomy and then take hat, or if we first take hats and then multiply. And finally, there is the star, but star is very, very obvious star. So these are functions, complex valued functions. There is well-defined complex conjugation. And now we want the element, the star of this element of quantum algebra to be just to correspond to taking first complex conjugation in the classical space and then taking hat. So now it makes it star algebra. And now there is this nice definition that given a star algebra, a state on this star algebra is a linear functional on this algebra, such that it is consistent with the star. It is positive definite. I'm sorry, here hat is missing. And also, I didn't maybe emphasize that our classical algebra, that our star algebra contains unity. But so actually, if you have some experience in algebra, you know that there is a big difference between algebras that contain unity and don't contain unity. So our algebra contains unity, and we want this state to be normalized in this way. Okay, so this is a very general notion used in so-called algebraic quantization. And now we add one more condition. We want our state to be diffeomorphism invariant, because we are doing diffeomorphism invariant theory. And if we assume this diffeomorphism invariance, then we have a nice theorem that there exists a unique diffeomorphism invariant state on the algebra, on this specific algebra here. Okay, is it clear? Are there any questions so far?
Hi, Jurek. Are you going to tell us how you get this theorem, and I mean, why it's true? Some flavor of it?
So well, it took us. Okay, so sometimes some honest mathematicians say that every theorem is sort of cheat because you assume as much as is necessary to prove this theorem. I think it's too strong statement. However, indeed, here it took us a while to formulate those conditions, to formulate those assumptions upon which this actually is true. So actually, in this case, one of the most important steps goes through. Now I'm trying again to get rid of. Okay, one of the most important steps goes through because of our definition of flux. So here we consider for flux variable. What's the definition of flux? This is, sorry. In the definition of the flux variable, we admit arbitrary smearing function. Well, which makes sense because for many reasons. I mean, it makes sense that when we have that we consider not only that we introduce those smearing functions. So at some stage of our theory, we just integrated those frame variables along codimension 1 surfaces. But then what we obtain is not really well gauge invariant, because we know that there are those gauge transformations I didn't write. And then such flux has very bad properties with respect to local gauge transformation. But if we introduce the smearing function, then the smearing function takes care of those local gauge transformations. So that's why it made sense. But this is due to the arbitrariness of those smearing functions. At some point, actually, we go back to this question from the introduction. So if such state exists, then we can define certain diffeomorphism invariant product between two smearing functions. But then if those since we admit continuous smearing functions, then this scalar product, doesn't exist, so it's identically zero. So then it shows that it gives us the action of our state on fluxes. So basically we show in this way that if we consider the element of this quantum algebra just given by flux, then the norm of this element is zero. And actually from this we are able to now it reduces all the possibilities, and we are able to show that then there exists exactly unique state. So what is the structure of this state? This state, so from this GNS, we can, by using GNS construction, we can define a representation of A. And then this representation takes the following form. So the Hilbert space consists just of functions of parallel transports of A. So those parallel transports, they become like positions in position variables in quantum mechanics. And we have certain measure for those functions. So we know how to integrate. And this is this measure which we use in loop quantum gravity, which in this way one can say the merges. I mean, historically it was the other way around. We first found this measure, but this is exactly this measure. And then the elements of this, the operators corresponding to holonomies, they just are. Whereas the fluxes, they act just by the classical Poisson bracket times I square root of -1 and h bar. So, well, so this is that representation, and then with this representation, once we have representation, then we have this state, because this state amounts to taking expectation value between. So this state here corresponds to the element of this Hilbert space, which is just a constant function equal to 1. And then taking expectation values between, just by sandwiching any element of the quantum algebra with this state, it gives us this state omega here. Okay, so this is this nice result. We say that in loop quantum gravity, there is this unique kinematical vacuum. This. Okay, so now what is the structure of this Hilbert space? So the structure of this Hilbert space is that of the inverse limit or inductive limit. So to organize this Hilbert space, we can do the following. So we can, so thus far I considered E1, En, they were just arbitrary paths in M. But a simple case is when those paths actually set a graph, which means when they don't intersect each other, except maybe meeting at the ends. And it also can be, at this stage, it can be open graphs. So it may be just a bunch of curves which don't intersect each other at all. So it may be open graph, it doesn't have to be closed in any sense. So if we fix a set of edges that set a graph, we can consider Hilbert space defined on this graph. And now, whenever we consider a refinement of this graph, so you can think of those graphs like of lattices in lattice theory. So we know what is refinement. So when we consider a graph which is refinement of our graph, then the Hilbert space defined on this smaller graph is contained in the Hilbert space contained in this refined graph. And now there is a very, very important notion for all the theory, which is cylindrical consistency. So what we are assuming is, well, I mean, it is quite natural. It doesn't have to be considered some extra assumption that since all those Hilbert spaces corresponding to graphs, they are subspaces of a single Hilbert space. So whatever our definition of operator is on this subspace, it has to be consistent with the definition of operator on a bigger subspace, because we are talking about operators defined consistency in the full Hilbert space. So that cylindrical consistency, it somehow connects all those different graphs and those different Hilbert spaces. And the emergence of graphs is here. It is often, as in this example which I gave in the beginning, it is often considered as a starting point for some discretized models. So one can choose just a single graph and build some theory on the single graph, and not bother about other graphs. But this is not loop quantum gravity. I mean, what we should do is when we define something, we should define it in the full Hilbert space, not just on a single graph. However, this is exactly implementation of one of those options. That one of those options is that, okay, so maybe this full Hilbert space doesn't exist. Maybe there's just this, maybe we should forget about manifold, about everything. Maybe we should just pick a graph and find whatever we want on this graph, and then maybe manifold will emerge later. On the other hand, there is the second option, that whatever we do, we should remember about manifold, and then we should do it in a consistent way, such that our theory, the structures we define, the operators we define, that they are defined on all the graphs, and they satisfy this cylindrical consistency. And only in this way we are able to take into account all the degrees of freedom which are encoded in the fields A. However, both approaches somehow coexist, and some people just choose just a simple single graph or some special kind of graph like triangulation, and then build something on this, and some other they bother about all the graphs and want to. So that may be compared to when you consider quantum field theory. You can either consider a Hilbert subspace of, say, one particle stays, and then define something on this subspace. But on the other hand, we know that the most interesting problems are related to all the Fock space, and we want operators and evolutions and states that are consistently defined in all the Hilbert space of all the excitations. Okay, so now let us. Okay, but now a few more comments about this, about what we did. So we also have the representation theory for compact groups. So we have the Peter-Weil theorem, which gives us the composition of space of functions on a single group. And on the other hand, we have representation theory, which tells us how to intertwine tensor products of irreducible representations into, again, irreducible representations. So using the two elements of the representation theory, we obtain orthogonal decomposition of our Hilbert space into finite dimensional subspaces. And each of those subspaces corresponds to the following data: to a graph, to some labeling of the edges of the graph with irreducible representations, and to some labeling of the vertices with irreducible representations. And now, if we consider the group G, if we consider example when G is SU2, and if we consider just trivalent graph, and if we label all the vertices by trivial representation, then we obtain a one-dimensional Hilbert space, and this is exactly what is known as Penrose's spin network. So in this way, we rediscover Penrose's spin networks and generalize them such that they give us orthogonal decomposition of our Hilbert space. So the spin networks you know about in the context of loop quantum gravity is just orthogonal orthonormal decomposition of that Hilbert space. Okay, we also have the gauge transformations. This usual Yang-Mills gauge transformations. A is subject. I'm sorry that I didn't write that also E is subject to those gauge transformations. In case of the E variable, we don't have the second term. And they act unitarily in our Hilbert space. We can also consider a subspace of our Hilbert space that consists of the gauge invariant elements. And however, so this is sufficient for vacuum gravity or for gravity coupled to scalar field. However, if we want to couple gravity to fermions, then we need also those. Then we need this bigger Hilbert space, this which is not gauge invariant because the matter. This Hilbert space, those quantum states of matter, they also transform with respect to those gauge transformations, and then they together constitute some gauge invariant elements. Okay, so now let us turn to closer to application to loop quantum gravity. So in case of quantum gravity, M is a Cauchy surface. So this is this three-dimensional surface on which we define a Cauchy data. The Lie group is SU2. And now the relation between the common geometric structures on this Cauchy, on the relation between this Cauchy data and our A and E fields is the following. So the E field is related to the if we undensitize the E field, then we obtain orthonormal frame. On the other hand, the connection is given by the metric connection plus beta times extrinsic curvature. And this is this little ugly moment, the emergence of this arbitrary constant beta. In the original formulation of Ashtekar, it was I, which was square root of -1, and then it naturally follows from the spin structure, and it is just the spin connection. However, since we were not able to define properly Hilbert space with beta equals square root of -1, on the other hand, we were able to define with some arbitrary constant beta. We just gave up and we accepted this beta, which is called Barbero-Mirzi parameter, because there were people who worked out the details of theory with beta. And actually, Tiemann was the person who pushed it forward. This construction with beta. But originally, when we were doing this, we thought that maybe thus far we do Euclidean gravity, and for Euclidean gravity, beta is just equal to 1. And maybe later we'll turn somehow to either weak transform, or in some other way we will also extend our definitions to beta equal square root of -1. The metric tensor, three-dimensional metric tensor, is related to the frame field in this way, where the scalar product K is just -2 trace. And also the constant h bar, in fact, if we do loop quantum gravity, it is replaced by 8 pi g beta times h bar. So everywhere when I wrote h bar, it should be replaced by this. Okay, and now our strategy is the following, that given an observable, let us start with the simplest case, given an observable, which is just some geometric object defined by our metric Q, by this metric here. We proceed as follows. So we write this Q in terms of E, but then we write every E in terms of the fluxes. So we write an expression which instead of Q gives our geometric quantity as some function of fluxes. Usually it also involves regularization. So actually only in some limit our expression becomes the original expression. However, then the advantage is that what is here on the right-hand side under the limit, it's automatically quantizable because we just replace fluxes by operators, and then this is operator. However, we have to make sure that our regularization is defined in such a way that this limit exists and that and it has suitable properties. I mean, it has all the invariants that it should have. So in this way, we define the area operator. And now the simplest case when we have a two-dimensional surface S, and the surface and quantum state is given by some function of some holonomies, but of some paths, but this only one of those paths begins on S, just touches this S with the end. Then the eigenvalues in such case of the area operator take this form. So this is 4 pi g beta h bar times this famous square root j times j plus 1. So they have something to do with the Laplace operator on SU2. So the conclusion is that edges contribute area. And now so that leads to very interesting interpretation, namely, if we now, there is a theorem. Let me first start with this theorem. Sometimes it's referred to Minkowski. So if we consider k vectors in R3, v1, v2, vk, and suppose that they sum to 0. And there is maybe some non-degeneracy condition about those vectors, that they are not contained in plane, or something like this. Then there exists a unique polyhedron which contains k faces, such that each face corresponds to exactly one of those vectors. It is orthogonal to this vector, and the area of this face equals the length of this vector. So obviously the opposite is true. That if we take polyhedron, then and if we consider vectors which are orthogonal to faces, and then if we make those vectors the length proportional to the area of those faces, then this should be 0. And this sometimes this can be seen in this way, that if you put polyhedron in water, then the pressure doesn't move polyhedron. So the forces which are, so the forces which act on individual faces, the force with which water and the pressure of water acts on those faces, it sums to 0. And now it leads to the nice interpretation of what is now a vertex of a graph. So if we consider some k edges meeting in a single point. By the way, does anybody know such an American writer, Kurt Vonnegut, and his book, Breakfast of Champions? Probably not.
I've only read Slaughterhouse-Five, but
but not Breakfast of Champions. Okay, so in Breakfast of Champions, there is a similar figure. However, it is referred to something else that I would even not have courage to spell out what it was. But that was because of Herr Vonnegut's nasty character. So if we consider a vertex of a graph, then there are such semi-coherent states which are exactly constructed from the similar data as this data defining polyhedron. Namely, those coherent states are constructed from, so to every edge there is assigned a vector in Lie algebra SU2. Those vectors sum to 0, and the area operator takes the eigenvalue of the area operator for small plaquette that intersects only one of those vertices, or each of those vertices contributes the area eigenvalue, which equals this. So that leads to this conclusion that perhaps vertices of our graphs, they are just polyhedra with whose faces have areas well given by the areas defined by the area operator. And then we can think that graph gives us the pattern how to glue those polyhedra. However, when we glue those polyhedra, then usually the shapes of faces coming from different edges, they don't agree. So it may be that one face is triangle and another one is square, and we have to glue them somehow. And then people call it twisted geometry or something like this, because they don't agree. On the other hand, the volume operator, so the simplest example for the action of volume operator is if we consider trivalent vertex, and then to each edge there corresponds one representation of SU2, and in each representation we have the spin operator. So J1 acts in H1, J2 acts in H2, J3 acts in here, and actually there are 3 spin operators per each representation. This I ranges from 1 to 3. Then the following interesting product and sum with the alternating symbol with epsilon gives us operator which basically from this operator we define the volume. So it is so this operator is actually, even though it's quite simple to write it, it is still not known the exact formula for the spectrum, and this operator is not so. I mean, it is known, but its properties are not worked out. So we can briefly say that the vertices contribute volume. So now some drawing. So you can see an example of such graph. So so we have the green lines are the edges of the graph. The graph has 2 vertices. So those edges, they contribute areas, while the vertices contribute volumes. Or in other words, we can view this like this, that our states are, in more general case, our states are given by some graphs, and then graphs are, we can, in order to consider this orthogonal basis, we can consider those p-network states defined by graph by labeling the edges by irreducible representation. So then each link contributes this area, and then each vertex, on the other hand, contributes a chunk of space. So this is the interpretation of that geometry. Okay, now but that was the simplest case. This was this quantization of the Q of the frame variable. But now if we want to consider operators which correspond to the A variable, where they are given by holonomies, but if we want to, but we know that with the connection variable, there is also related connection curvature, and this is most interesting because it is because the constraints, the gravitational constraints, the gravitational curvature involves this curvature of this connection. So we replace. So the idea is that we replace components of F by loops and shrink them. However, now there are some nice moments, but there are some problems. So what is nice is there is this magic result that if we consider diffeomorphism invariant state, then actually shrinking the loop is then this everything is invariant with respect to shrinking loops, so we can easily go to the limit. But okay, and even nicer is that those diffeomorphism invariant states that there are solutions to the vector constraint of gravity, of vacuum gravity. However, the problem is that they are not normalizable states. Okay, but now we also have, for this, we know how to cure it. So actually, we know how to define a space of diffeomorphism invariant states for which we can define a new product. And it's quite natural. We use so-called ridging map for this. However, the unsolved problem is that we can replace a component of the curvature F by a loop in infinitely many different ways. And then depending on what way we choose, we obtain different operators. And some people compare this ambiguity to the ambiguity of infinitely many renormalization constants. So they say that we just replace the non-renormalizability of gravity by infinitely many patterns for quantizing F. Now, if we couple the matter fields, then there are some new phenomena. There are two possibilities. One possibility is that we actually swallow the matter fields. So remember that we have still that if matter fields are coupled to gravity, then we have those 4 constraints. We have 3 vector constraints and 1 scalar constraint. So we can solve those constraints in each of the constraints in favor of one field. So it means that just naively counting, given 4 scalar fields, we can actually swallow those scalar fields by solving the constraints. And then they disappear from the theory, but just theory has a little more degrees of freedom, but those degrees of freedom are sitting in gravitational field. We don't see those matter fields anymore. Another possibility is to introduce a new background independent quantization for those matter fields, which we also do. Now there is some other property which I didn't mention, basic and mathematically very well understood, namely if we can go back to this kinematical Hilbert space and ask about diffeomorphism invariant operators, then it turns out that again there is a theorem that diffeomorphism invariant operator has to preserve every graph by graph. So you could ask, so in what way we define those operators corresponding to F, to the curvature of the gauge connection, of the connection variable. So it turns out that we actually either we cannot do it in diffeomorphism invariant way, or we do it in diffeomorphism invariant way. However, if we go already to some dual space in which we consider diffeomorphism invariant states. But now Giesel and Tiemann, they actually came to another conclusion. Namely, what they did is they considered loop quantum gravity coupled to Brown-Kuhar model, which contains 4 scalar fields. Then they did what I just described. They swallowed those scalar fields by the constraints. And then the result of such a procedure is that we obtain a theory which is defined again by those variables A and E. So we can apply all those techniques of loop quantum gravity, which I just described here. However, in this theory, we don't have any more diffeomorphism constraint, which means we don't have to go to diffeomorphism invariant states. We still have diffeomorphisms, but they are diffeomorphisms in the space of dust. So this Brown-Kuhar model is the model of dust coupled to gravity. Dust is described by certain 3-dimensional abstract manifold of dust. So the molecules of dust, they set a 3-dimensional manifold, and then this theory is invariant with respect to diffeomorphisms of dust. So now we obtain diffeomorphism invariant theory defined in our loop quantum gravity framework, but now we want all the operators, including the Hamiltonians, to preserve graphs. So that led Giesel and Tiemann to the conclusion that then actually there's only one graph, or that, in other words, that theory just decomposes into theories on single graphs, and that those graphs are not anymore connected with each other by any operators, because we are allowed only to consider operators that preserve those graphs. When we do loop quantum gravity, then we also face this fundamental question. Namely, in everything what I described thus far, I assumed, so we were very conservative. We assumed that there is a underlying manifold, and we quantized everything on this given manifold. But there is also a big pressure of community, and actually many people think about this, that manifold itself should also emerge from quantum theory. So that would lead to this option when we actually start with some more primitive structure, with some graphs or some graphs, and then which are not contained in any manifold, which are just given abstractly, and then this manifold maybe will be derived in a limit. But if we are rigorous mathematically, then we should answer ourselves whether we want to assume the existence of manifold and whether there exists manifold for everything what we do, or whether there is no manifold and this manifold will emerge later as some semi-classical property. Okay, so this is, I think, I reached the end of my talk. Thank you. Hello.
Questions, please. Any questions online? Yeah.
Find them. Yeah. So I'm a little confused about the statement that you made towards the end and also earlier, that each graph preserves this, the diffeomorphism is diffeomorphism invariant, and you can't go from one to another. The construction of the graph, of course, given a manifold, you can imagine multiple graphs that would represent that manifold. And the scale of how big the graph is, how connected it is, all of that should contain information about the about the manifold. So when you say that there's just a single one, and you can't, and that's the diffeomorphism invariant state, so to speak, on that graph, do you run into some contradictions, or do you think that just a single graph will have all the information for the manifold?
Okay, so I don't belong to this group of people who think that we can describe that we can describe well manifolds by a single graph. So certainly I don't know the answer to this question, because I mean, I don't like this approach. However, this is, once again, the logic is that we have that Hilbert space of states which are defined on all possible graphs. So if we want a generic state, this state will be maybe infinite composition of, may have infinite terms on infinite, corresponding to infinitely many graphs. And still our operators can map such state into yet different state defined on yet different graphs. However, if we restrict ourselves to diffeomorphism invariant, so graphs are not diffeomorphism invariant. Graphs are, but if we restrict ourselves to operators that are diffeomorphism invariant, for instance, like total volume of this manifold, then such operator will preserve every graph. So we may say that as long as we describe physics only by diffeomorphism invariant operators, then, and we start with a state which is defined on a single graph, then we reduce our theory just to this subspace of states on the single graph. So in this sense, we don't need the other graphs, because our theory is reducible to this theory on this graph. But it doesn't mean that from this single graph we can uniquely reconstruct manifold.
Any other questions? I have a short question. So when you say discretization of space-time, is it only relevant at Planck scales, or at the horizon scale of black holes, somehow discretization is required, or it will give us some understanding of black hole horizons?
In quantum gravity, we don't have a good, I mean, we don't see horizons on the quantum level. So what we do, the best what we do is we introduce some sort of hybrid quantization. So we build in classical horizon, and then we have some quantization of geometry of horizon coupled to quantization of bulk. But this is so there are very nice models. You can do a lot. However, those horizons, one has to be fair and say that those horizons don't emerge from quantum gravity. We just assume that, so we independently quantize horizon and independently quantize bulk, and then we make from this model of quantum black hole.
Thank you. If there are no more questions, let's thank Jerzy again.
Thank you.